Hello, good evening. Hi, my name is Boris Jeremic. I'm currently in Zurich, Switzerland. This morning, this morning for them, this afternoon, this evening for me, with me are Dr. Han Yang and in Davis,
Hello.
California, and Mr. Heshan Wang, who is actually going today
Hello.
to uh, talk about intrusive probabilistic modeling. In this particular case, he's going to give us an example on how is this done for a particular specific location with two faults and whatnot to estimate risk of unwanted performance. Today is Wednesday, May 20th. It's almost 8 p.m. for me. It's almost 11 a.m. for them. So Heshan, please. So we have issues with internet. So we're gonna, once we go into sharing screen, Heshan's screen, we're gonna shut down our camera so we don't spend too much of the internet. So Heshan, please go ahead, share your screen.
Okay. Yeah.
And we'll do the same thing as before. If I have a question, I'll wait for you to finish, and then I'll say, and then
Okay.
I'll ask a question. So I'm shutting down my video. So guys, shut down your video. Okay, good.
Yeah.
Yeah, go ahead.
Okay. Yeah. Yeah. So yeah, good morning, everyone. So in our previous lectures, we have talked about the theory and examples of the uncertain quantification. And today we're going to show how do we apply this uncertainty quantification techniques into the time domain framework for probabilistic seismic risk analysis. So at the beginning of the presentation, I will give you a brief introduction on the probabilistic seismic risk analysis, and then I will show you our novel framework for doing that, and also an illustrative example. So this is our problem. We have an uncertain seismic source propagating through uncertain paths onto uncertain site and structure system. And we want to design and analyze our engineering system to have an acceptably small probability of engineering demand parameter or damage measure or loss. For example, a typical engineering demand parameter for engineering system for like building structures can be interstory drift of your building system. And in order to do that, currently the state-of-the-art framework for probabilistic seismic risk analysis consists of two parts. Number one is the probabilistic hazard part, which is considering the uncertainties of the ground motion. And number two is the structural fragility analysis part, which handles the uncertainties in the structure system. And the exceedance rate of, for example, engineering demand parameter is calculated as a convolution of the seismic hazard analysis and the structural fragility. And this has been a very powerful tool that allows us to do objective and quantitative decision making. However, it does have several significant issues. So number one is the issue of using intensity measure in the current framework. So intensity measure is supposed to serve as the proxy of the damaging ground motion onto the engineering system. However, the problem is that the single intensity measure could represent all the uncertainties in the ground motion that are critical or important to the structure damage. For example, for the building system, the typical intensity measure can be the spectral acceleration at the fundamental period of the structure. However, we know that this single intensity measure cannot capture the structure nonlinearity response. For example, when we consider the seismic risk for the structure collapse, where the structure is largely deformed with a significant nonlinearity, the period of the structure has been significantly shifted, and the spectral acceleration fundamental initial period cannot capture this nonlinear effects. And also, this spectral acceleration as the fundamental period cannot capture the higher mode response, which can be quite important for the high-rise buildings. And actually, for any engineering system, that cannot be simplified as a single degree of system, linear elastic, single degree of freedom system. A spectral acceleration at the fundamental period of the structure does not work well. And this is especially true for geohazard, and it has been and it has been practically difficult and to choose a proper intensity measure for many geohazard analysis. For example, people have been contentiously arguing that whether we should use average intensity or peak ground velocity or cumulative absolute velocity for dam embankment risk analysis. And more fundamentally, fundamentally, we think that there is a miscommunication between engineering seismologists and earthquake engineers. Back in 1970s and 1980s, we as earthquake engineers, we have a very limited numerical tools. So we have to do the structure analysis based on linear elastic friction domain analysis. At that time, the engineering seismologists, they interpret their ground motion result into a spectral acceleration. However, nowadays, we as earthquake engineers, we have this very advanced nonlinear time domain simulation techniques. However, engineering seismologists, they still give us the spectral acceleration, which is not compatible to what we need. So the second issue,
Heshen, can I add, Boris, here, can I add
yeah,
one
yeah,
comment? So go back to the
yeah,
previous slide. So essentially there are all these, I mean, the seismic motions are seismic motions and they come very uncertain. And to be
yeah,
able to pick up one single parameter
yeah,
from those motions or one single type of analysis is very hard. And that's why there's all this discussion about which is the proper intensity measure, because different structures, different systems, different stiffnesses, different elastic,
yeah,
non-inelastic, and so on, they will respond
yeah,
differently to these different intensity measures. And so it's
yes,
really not very convenient or not very engineering to pick up one of them, although it is convenient in the sense that it simplifies life. But in doing that, you make complication on the other side, because you essentially
yes,
miss some other important parameters, and that's the main issue. That's
yeah.
what we are trying to solve here.
Yeah, and also as professor mentioned that since the engineering seismology, they only provide hazard analysis for the single intensity measure, and when we earthquake engineers, when we do the structure analysis, we still need the time series. So then there is the
Yes.
whole ad hoc technique to how to select the ground motion based on the single intensity measure, which is a lot of flexibility and a lot of uncertainty can go on. Yeah.
Yes, go ahead, please.
Yeah, and the second issue is the use of the Monte Carlo simulations in the current framework. As we know that Monte Carlo simulation you do
So
not need to modify
Heshen,
your underlying
we were
deterministic solver.
we were losing you. Can you go back to Monte Carlo? We were losing your voice. I guess
Okay,
something is wrong with the internet.
okay. Yeah, I mean the second issue is the use of the Monte Carlo simulation in the current framework. So as we know that Monte Carlo simulations is a non-intrusive approach. You do not need to modify your underlying deterministic solver. However, it has a very slow convergence rate. And also, it's very hard to use in Monte Carlo simulation to get a stable tail distribution, which is very important for risk analysis. But unfortunately, in our current framework, for example, we do use incremental dynamic analysis to derive the structure fragility curve, which is essentially a Monte Carlo type simulations. You might require to run hundreds of even thousands of nonlinear dynamic structure analysis to get a structure fragility curve. And this is impractical for very large and complex realistic engineering earthquake soil structure interaction system. And this is why we also need for the uncertain seismic wave propagation approach.
Heshen, I'm sorry, Heshen, stop. We're losing you. So
Okay.
you said it's impractical, and then the voice disappeared. So go back to this. Yes, it says that the internet is
So,
unstable.
oh,
Oh,
impractical for, you hear me now?
no, we lost you. We don't have you. Good evening. This is our second try. We just lost the internet a few minutes ago.
Oh, okay, you are recording.
I think I'm recording. I think I remember to click on record. Yeah, I'm recording.
Okay.
Um, this is our easy lecture series. Today is May 20th, 2020. It's 5 minutes before 8 here in Zurich, Switzerland, where I am. And today with me are Mr. Heshen Wang, who's going to be talking
Hello.
about probabilistic risk analysis, seismic risk analysis, and Dr. Han Yang, who is also there, who talked before some of his issues with energy dissipation. He's going to give more lectures in near future next week or so. It's again, as I said, it's 5 or 4 minutes before 8 here p.m. or 1956, as they say here, and then it's 11. No, not 11. It's 10:56.
10:56.
10:56 in Davis. 10:56 in the morning. Okay, so Hesham, please start sharing your screen,
Okay.
and we can get going from beginning.
Okay.
I need to hold on. I think. Oh, okay, it works. Okay, good. So go
Uh,
from beginning. Yes, please.
okay. Yeah. I can shut down my video. Okay.
And
Yeah.
I'm gonna shut down my video. That's right. We are gonna shut down video just because we don't have enough bandwidth in the internet. So go ahead, please.
Okay, yeah. So in our previous lectures, we have talked about the theory and the application of the uncertainty quantification. And today, we're going to show the examples of how to apply this uncertainty quantification techniques in a novel framework of a time domain framework for probabilistic seismic risk analysis. So this is an outline of my today's presentation. I will first give a brief introduction about the probabilistic seismic risk analysis, and then I will show you a new framework and an illustrative example of this new framework to do the risk analysis. And so this is our problem. We have an uncertain seismic source propagating through uncertain paths to the uncertain site and eventually to your uncertain structure system. And we want to design our engineering system or analysis our engineering system to have a acceptably small probability of engineering demand parameter, damage measure, or loss. For example, a typical engineering demand parameter for building structure can be the interstory drift. And to solve such a problem, the current state-of-the-art framework for seismic risk analysis consists of two parts. Number one is the probabilistic seismic hazard part, which considers the uncertainty in the ground motion, and the number two is the structure fragility part, which considers the uncertainty in the structure system. And the exceedancy rate of your engineering demand parameter is calculated as the convolution between the seismic hazard and the structural fragility. So this has been a very powerful tool that allows us to do objective and quantitative decision making. However, it does have several significant issues. Number one is the use of intensity measure in the current system. So intensity measure is supposed to have a is supposed to serve as the proxy of the damage ground motion onto the structure system. But the problem is that does the single intensity measure can capture all the uncertainties in the ground motion that is critical or important to the structure damage. For example, for building structure, spectral acceleration at the fundamental period of the structure has been used as the intensity measure. However, this intensity measure cannot capture the structure nonlinearity. For example, when we talk about the collapse of the building structure, um, where the structure can be largely deformed with a significant nonlinearity and a period shifting developed, then the spectral acceleration at the fundamental period of the structure cannot capture these nonlinear effects. And also, the spectral acceleration at the fundamental period cannot capture the higher mode response, which is pretty important for the risk analysis of high-rise buildings. And actually, for any engineering system that cannot be simplified as a linear elastic single degree of freedom system, spectral acceleration as the fundamental period does not work well. And it's actually practically very difficult and contentious to choose a proper intensity measure for many engineering systems, especially for geohazard system. For example, people has been contentiously arguing that whether we should use areas intensity or peak ground velocity or cumulative absolute velocity for dam embankment risk analysis. And more fundamentally, we think there is a miscommunication between engineering seismologists and earthquake engineers. You know, back in 1970s and 1980s, we as earthquake engineers, we has very limited numerical tools and computational power. So we have to rely on linear elastic friction domain spectral analysis. So at that time, engineering seismologists, they interpret their ground motion result into spectral acceleration. However, nowadays, we as earthquake engineers, we have been able to do this very advanced nonlinear time domain simulations. But engineering seismologists, they still give us the spectral acceleration. So this is just not compatible with what we need. And the second issue is the use of Monte Carlo simulations in the current framework. As we know that Monte Carlo simulation is a non-intrusive approach, which means that you do not need to modify your underlying deterministic solver. However, it has a very slow convergence rate, 1 over square root of n. And also, it's very hard to use Monte Carlo simulation to get a very stable tail distribution. And we know that in risk analysis, it is the tail distribution that really controls the risk. But unfortunately, for example, in our current framework, we do use incremental dynamic analysis technique to derive the structure fragility curve, which is essentially a Monte Carlo type simulation. You might need to run hundreds or even thousands of nonlinear dynamic structure analysis to get a structure fragility curve. And this is impractical for complex nonlinear large engineering system in practice. And the same issue also exists in uncertain seismic wave propagation over regional geology. Um, as we know that nowadays we have already been able to do this deterministic physics-based earthquake ground motion modeling of regional geology using numerical tools like CyberShake from Southern California Earthquake Center. However, if we want to considering the uncertainties in such a simulation, for example, considering the uncertain source and uncertain uh, ground parameters, then it has been estimated that for example, for Los Angeles, we need to run over 20,000 seismic scenarios, and that will take 300 million CPU hours and over 100 years to finish. So this is just a computationally prohibitive expensive.
Yes, can I
Yeah,
add a comment? So please go back to the previous slide. So
okay.
essentially, yeah, previous slide. So essentially, what used to be the case used to be that you had to pick up one single intensity measure that is supposed to be the most devastating or the most important intensity measure for your type of
Yes.
structure. This is not possible. Different structures, different stiffnesses, different soils, different interaction modes have different intensity measures, different types of behavior that are going to be important. So this is always contentious. This is always a big discussion about should it be peak ground velocities, peak ground accelerations, should be spectral accelerations, and they're all important. Some are more important than the others. So what we're really doing is we're replacing all those choices with a single approach that we're going to talk about in a
Yeah.
second. And go back to the next
Yeah.
slide. So the Monte Carlo it's nice, it's simple, it's non-intrusive, so you can use already available tools, but it takes a lot of runs to get stable tails, and usually it's done as a deterministic, and nothing with geology and wave propagation is deterministic. So we don't really know what the material properties of some shallow and deep geology rock and soils are. So it needs to be done many times with Monte Carlo, and this present approach is actually going to replace that need. So this is a nice illustration, the 100 years to get somewhat proper estimate of what the probabilities of motions are going to be in LA scenario. Yeah, we do not have 100 years to wait for that. So yes, go ahead.
Yeah, that's true. Yeah, so as the professor mentioned, because of these current issues, so we have proposed a novel framework, which try to improve the current framework. For example, instead of using intensity measure, a single intensity measure as a simplified proxy of ground motion, we try to consider all these uncertain motions in time domain and characterize and propagate them as a random process. And instead of using deterministic Monte Carlo samplings to do the uncertainty propagation, we have been able to do the direct intrusive uncertainty propagation that could directly propagate the uncertain motions to the uncertain structures, which will give us a and complete and accurate dynamic probabilistic structure response. And so this is our framework. So we will again start with the standard seismic source characterization part, but then for each of these characterized seismic scenario, instead of go to GMPE of the choosing intensity measure, we go to the stochastic modeling of the underlying Fourier ambient spectrum and the Fourier phase spectrum. And from that, we can use inverse Fourier synthesis to get the time domain uncertain motions. And on the other hand, we will also have some uncertain structure parameters in the engineering system. So we will characterize both of these uncertain motions and uncertain structure parameters using a unified technique we presented before. That is the Hermite polynomial chaos Cahunen-Loewy expansion. And with this, once we characterize both of these input uncertainties, we can do the uncertainty propagation using stochastic finite element method, which you can get the whole probabilistic dynamic structure response by a single simulation analysis. And from that, we can get the structure structure failure probability of any chosen engineering demand parameter. And we combine this failure probability with the scenario rate information that will give us the ETP hazard and seismic risk. And
Can I just go back? Can I just say, so the key point that you're making here is that it's a single shot. We essentially solve the system in one shot. Now, I do
yeah,
not want people to get an idea that it's that simple. That single shot, those equations become much larger because
yeah,
we have both spatial and time domain, and we have a probabilistic domain because we expand with polynomial chaos into probability domain. So the system of equations, the system that we analyze becomes much bigger, but the solutions are more accurate and it can be
yeah,
done more efficiently. And some of those subjective maybe choices, some objective, some subjective choices of intensity measures do not have to be made because we essentially, this methodology takes into account all possible uncertainties. Yes, go ahead, please.
yeah, that's true. Yeah, and we do not make any assumption for the ground motion and also
Yes,
for the structure parameters. Yeah.
yes,
And yeah, a little bit more explanation on the stochastic ground motion modeling part. So as I mentioned that the key point is to shift from the modeling specific intensity measure to the two fundamental characteristic of the uncertain motion. That is the uncertain Fourier empty spectrum and uncertain Fourier phase spectrum. And recently, the engineering seismologists really recognize the great advantages of using Fourier empty spectrum as a new interface between the seismologists and the earthquake engineers, and they have developed the GMPE for the marginal median and the variability of the Fourier empty spectrum, and also the interfrequency correlation structure for the uncertain Fourier empty spectrum. And Professor Abrahamson and his student also established a GMPE for the stochastic Fourier phase spectrum. And as it has been envisioned by Professor Abrahamson, in the next 5 years, one of the major change in the seismic hazard part is to shift from spectral acceleration to Fourier empty spectrum. And the framework that I presented before has been such a framework that can be consistent to such a to such a change in seismic hazard part. We can directly provide such a framework that can directly propagate these uncertain motions to your uncertain structure system, which will can directly do the seismic risk analysis. So here I'm showing the three realizations that simulated using the uh, presented methodology in this slide, and for the single scenario magnitude 7 and the distance 15 kilometers. And we might have, for such a single scenario, we might have several hundred of such realizations, and we can calculate the spectral acceleration of these realizations and check these realizations with the commonly used GMPE. As you can see here, the median behavior of our simulated ground motion is consistent and not biased compared with the GMPE. And here in this plot, I'm showing you the standard deviation of the spectral acceleration for the simulated ground motions with the sigma in the current GMPE. As you can see that we also have a very consistent amount of the variability carried among these simulated uncertain ground motions. And now I'm showing you a illustrative example that apply this presented framework to do the risk analysis. Say we have an engineering site and two seismic fault nearby, and the fault one is supposed to be the San Gregorio fault, and the fault number two share the same parameter as the Calaveras fault. And we will considering the uncertainties in the segmentation of the fault, the slip rate, the rupture geometry, and so on. And we will perform the standard seismic source characterization for these two faults, and we will end up with 371 total seismic scenarios for this engineering site. And as you can see here, the dominant scenarios are distributed among magnitude 5 to 5.5, 6.5 to 7, and the distance 20 to 40 kilometers. And for each of these single scenarios, we will perform the stochastic ground motion modeling, the time to simulate these time domain uncertain motions. And then we will quantify all these time domain uncertain motions using Hermite polynomial chaos and Kaplan-Loewy expansion. As I
can I add a comment? Can I add a comment?
Yeah,
Go back to the previous slide. I'm sorry. Can I add a comment?
yeah,
Yes. Go back. So
yeah,
this is a real site in California.
yeah.
We won't say where it is. I think we got this from Norm, right?
Yeah, some parameter are got
Yes,
from
some
Norm. Yeah,
parameters we got from Norm. This is a real site, so we are really going through a realistic site with realistic faults, with realistic probabilities, and the results you're going to see are going to be very realistic for a given building. Again,
yeah,
any building can be analyzed, or any soil structure system can be analyzed this way. Yes, go ahead, please.
yeah. So yeah, we have presented before, how to do the Hermite polynomial chaos calculating logic expansion to quantify such a random process. And here, we just verify that our Hermite polynomial chaos expansion can capture both the marginal mean and standard deviation, and also the correlation structure of the input uncertainties in the ground motion. And we also considering the 8-story nonlinear shear frame structure in the engineering side, and we were considering the uncertainty in the structure parameter. Here we have been using a Armstrong-Frederick kinematic nonlinear Armstrong-Frederick kinematic hardening with a vanishing elastic region. This model to quantify the hierarchical behavior between the interstory restoring force and interstory drift, and we considering the 15% of the coefficient of variation for the structure parameters, and also exponential correlation for the structure parameters. And we will perform the uncertainty propagation of this uncertain motion to such an uncertain structure system using the stochastic finite element analysis that we presented in our previous lectures. And here we can obtain the dynamic probabilistic response of the top floor response of the time evolving mean and standard deviation of the structure response. And we
Okay,
can choose
I'm sorry. I'm sorry. Go back. So
uh,
this is an example where we essentially do just the structure, shear beam, essentially.
uh,
But this is fully. This is in 1D. This is how far we have gone so far. This can be easily. You can just add a few more layers now, and this can be easily done as a solid structure system. And then we're working on expanding this into 3D. So we should be able soon enough to do a full 3D solid structure system, which is going to be a little bit more involved computationally, but so be it. But this is just an illustration of an uncertain shear beam, in this case, that is accepting some uncertain motions at the bottom and has uncertain has an uncertain material, and that material is modeled using this Armstrong-Frederick nonlinear model with given probabilities. So yes, go ahead, please.
yeah. And now once we have the probabilistic dynamic structure response, we can choose any engineering demand parameter. For example, here we're choosing the maximum interstory drift ratio as the engineering demand parameter, and then we can get the evolution of the PDF of the chosen engineering demand parameter, and we can see how the PDF changed among the different time steps, and also how the PDF what's the PDF of the maximum interstory drift among the different floors, and also the whole structure. So by combining this, and then obviously we can get the failure probability of the from this probabilistic structure response. And then by combining this probabilistic structure response with the seismic scenario rate information, we can get the annual exceedance rate of the engineering demand parameter. And this is our EDP hazard. And this can be directly used for seismic risk. And similarly, we can also choose the peak flow acceleration, because some building might be sensitive, or some structure system might be sensitive to the acceleration control. We can also get the PDF of the peak flow acceleration at the different floors and the overall whole structure, and we can also get the ETP hazard for the peak flow acceleration. And since now we have a whole probabilistic structure response, we can even create the joint PDF of the uh, two engineering demand parameter. For example, the maximum interstory drift ratio and the peak flow acceleration. And from this joint PDF, we can do the seismic risk analysis for multiple engineering demand parameter as the failure criteria. For example, we can calculate the seismic risk for damage measure defined on multiple EDPs. The damage measure defined on maximum interstory drift ratio greater than 1%, or peak flow acceleration greater than 1 meter per second. That seismic risk is about 4.2 times 10 to minus 7. And on the other hand, if we define our damage measure as the maximum interstory drift ratio greater than 1% and peak flow acceleration greater than 1 meter per second, you will get a much lower seismic risk. That is 1.71 times 10 to minus 3 per year. As you can see here, depends on how do you define your damage measure, and on your these risk values uh, for the damage criteria defined using multiple engineering demand parameter can be quite different as what we are currently doing, for a single engineering demand parameter. They can have some significant difference. So and in the current framework, you cannot consider in the multiple engineering demand parameters, especially in your fragility analysis. So but now we can considering any EDPs and
Yeah.
any damage state. So this is a very good advantage for our framework. And
Can I just add? So you said 10 to minus 7. 10 to minus 3 is the 4 times 10 to minus 3. But go back
yeah,
1 or 2 slides. Essentially,
uh,
essentially the point is that you get full. Go one more slide. Full
uh,
probabilistic response of the whole structure, every single component, every single floor, and then you can choose what you want to see, how you want to combine them, and how you want to visualize them. And you get the full PDF, full probability density function for each of these unknowns, for each of these degrees of freedom. And then you can present, you can integrate them to get fragilities, to get cumulative density functions, and so on. So go for it,
yeah.
because that's exactly where you can combine these.
Hmm.
You can combine interstory drifts and peak floor accelerations. You can combine them with other things. Depends on the type of structure you have. Yes. So go ahead.
Yes. Yeah. Yeah. So essentially, we provide more information that you can post process whatever the piece of the risk that you care about.
Yes.
Yeah. And with that, yeah, I think that's all what I have today. And I want to give thanks to my collaborators and this funding resources. And you can, if you're interested in this technique, you can check out the Real ED simulator system. And thank you for your attention.
Thank you very much. Let's turn on our cameras and you stop sharing your screen.
Okay.
Guys, turn on your camera so we can
Okay.
find the audience. And this went well. We don't have any interruptions in internet, so we'll pause this and then we'll continue doing this, and we'll see you back again. Thank you.